Dear colleagues and students, this is Dr. Uğur Güven, happy to present my paper on interstellar travel plausibility in this digital version of the International Astronautical Congress in 2020. As you may be aware, this is the beginning, the dawn of time, the dawn of civilization, which we know started in Göbekli Tepe 9,000 years ago. People have been looking up at the twinkling lights in the skies and wondering what's there and wondering how they can perhaps reach there. There's a good French expression for this, le rêve d'étoiles, or the dream of stars. It has been one of the dynamo or the driving forces of mankind since the beginning of time. Of course, there has been a lot of science fiction stories as well on how to reach stars. There are a lot of famous writers like Arthur C. Clarke, Isaac Asimov, Balboa, who have been very explicit in explaining their views about how stars can be reached through a variety of means: antimatter drives, warp drives. Obviously, Star Trek with its warp drive and Star Wars with its faster than light drive has been an interesting science fiction genre that has always given hope to humanity that perhaps science one day can catch up to science fiction. So let's take a look at the nearby stellar systems. Obviously, the closest star we have to our system is the Alpha Centauri, which is roughly about 4.3 light years away. It's comprised of a multiple star system. Actually, the closest star is about 4.26 light years away, which is Proxima Centauri, which is in the Alpha Centauri system. Then we have Bernard star, which is roughly 6 light years away, 5.96 to be exact. We have Wolf 359, which is 7.78 light years from Earth. We have Lalanda 21185, which is about 8.29 light years from our solar system. We have Sirius, which is 8.58, and at the edge of the 10 light year system, we have Ross 248. Basically, all of these stars are within a 10 light year radius of our sun. What this basically means is that, for example, to reach Alpha Centauri system, which is 4.3 light years away from Earth, if you had a spacecraft which could travel at the speed of light from Earth, or our solar systems to be exact, all the way to Alpha Centauri, traveling at the speed of light, it will need 4.3 years to pass before you can reach Alpha Centauri system, another 4.3 to come back. So basically, even in the best case scenario, if you had a spacecraft that can fly at the speed of light, it would take 9 light years to go and come back to Alpha Centauri system. Bernard star, which is also quite interesting because there have been a lot of controversy as to whether there could be life on Bernard star, which is roughly 6 light years away, has been another exciting destination that mankind has wanted to go to. Of course, we know from Einstein's equations, at least for now, because in science nothing is set in stone, everything can change, always new information can override old information. But as far as we know from physics from the time of Einstein, that light year is impossible to reach because there will be such a huge mass expansion as you reach the speed of light. It will be impossible. You would need infinite amounts of energy to be able to accelerate further. So at best guess, we will be able to reach semi-relativistic speeds. So even the nearest star system, Alpha Centauri, which is 4.3 light years away, would probably take 6 to 8 years to reach with semi-relativistic speeds, which are lesser than the speed of light. But eventually, I do believe that science will catch up and it will be possible to reach other stellar systems. Of course, there has been a lot of work already, especially the British Interplanetary Society has been very active in trying to look at different forms of interstellar travel. There has been a lot of work from various space agencies as well. Project Daedalus, Project Icarus, Project Orion have been some of these important projects, mostly depending on fusion drive, basically, which is a spacecraft that uses nuclear power, fusion to be exact. Fusion, as you know, is the same process that happens in our sun. Helium molecules come and bind together. Hydrogen molecules come and bind together to form helium. and during this fusion, some of the mass is converted into energy. That's why our sun shines so brightly. That's why we have energy from our sun. So it's possible to use same type of energy to overcome and reach high speeds. But unfortunately, fusion requires such high amounts of temperatures. It's very hard to contain them, even using some sort of a magnetic containment shield, though a lot of work is going on this regard. Now, basically, the key to success is having a high specific impulse. As you can see in the slide, specific impulse is exhaust velocity divided by g. Or basically, as you can see, the exhaust velocity on the upper equation, highlighted in white, depends on a variety of factors, but the most important factor is the TC parameter you see there, which is the combustion temperature. As you can see, in order to have a high exhaust velocity on a spacecraft, it's very important to have very high combustion temperature. So higher the temperature goes, higher the speed. So that's why we're always looking at nuclear propulsion systems as an alternative, because with nuclear energy you're able to reach high speeds because you're able to reach high temperatures. We have fusion, we have fission. The fusion is obviously going to give you much higher speeds because they have much higher temperatures, but it's very harder to contain. And fission rockets, nuclear thermal propulsion, is able to get lower temperatures but still high enough speeds to go someplace. So if you look at our requirements for interstellar travel, the first requirement is obviously high specific impulse. This again, it can be reached easily through nuclear means. But you can also use more other forms of propulsion, like ion propulsion, where you accelerate the ions by creating a charge. Acceleration and discharging of these ions from the rear of the spacecraft gives you forward momentum. And of course, we have more exotic means of interstellar travel available, such as warp drive. And NASA is working on such a drive called Alcubierre drive for a long time now. Mathematically it's possible, but technologically it's going to require a lot of time. The durability of the spacecraft is very important. You need a continuous energy source, because you can't undergo an interstellar mission unless you have an energy source that will provide the necessary electricity for your onboard systems for a decade or more. You need an interstellar propellant, which is light to carry. Hydrogen is a very good choice, because hydrogen is something you can also mine from the interstellar space. You need proper shielding for interstellar particles, and especially to the radiation that will be present in interstellar space. When you pass the heliopause of our solar system, which is the boundary of our solar system, basically you'll be exposed to interstellar radiation. Obviously, you need advanced navigation systems, advanced computer systems to process all the data, and you need advanced sensors to navigate through the interstellar space. So, thank you very much. This is my presentation. You can go to my website. I have papers prepared on various destinations like Lalanda 21185, Wolf 359, Bernard Star, Alpha Centauri. Feel free to take a look at my papers. Feel free to take a look at my projects. My email is drgwen@live.com. So I thank you all for listening to me, and I wish you your happy journey in the International Astronautical Congress.